Today's tinkering is accompanied by Lake of the Woods Brown Ale from Lake of the Woods Brewing Company in Kenora, Ontario. They describe it as a malt-forward pub-style brown ale, a nice simple ale, but true to the style. Even though their headquarters and main location is in Kenora, they also have a taproom and brewery in Winnipeg, and I've been to that one. It's pretty cool. And surprisingly, they also have a taproom and brewery in Warroad, Minnesota. So my American viewers can actually get this beer. It's not often that happens. But this particular one was brewed right here in Canada. So today, I'm going to be playing a little bit with this cheap PC cooler that I got in the most recent mailbag. I didn't buy it for computer. I bought it to try and work on upgrading my DC load that I built some time ago. This thing needs a lot of help. It's underpowered. It can only do about 3 amps. I'd like it to do a lot more. The resistor overheats. The MOSFET doesn't get too bad, but I'd like to put a bigger MOSFET on here so I can handle more power. And the cooling of all of that. That's why I thought I would get one of these and see if I can make use of it. Now, the disappointing part that I hadn't thought about when I ordered it was that the heat transfer block is really tiny compared to the power resistors that I'm going to use. So I've got to come up with a plan for that, but that's not what I'm doing today. Today, I want to see if I can control this by PWM. This is a 4-wire PWM controlled fan, which is very standard in PCs. The 4 wires, I'm not sure which ones they are, but the 4 wires are DC plus and minus, a tachometer output pin, which I think I'm going to ignore for now because I don't really need that, and the PWM input pin, which controls the speed of the fan. I don't have a ton of information about this, but according to underneath the sticker here, it is a 12 volt fan. 2000 RPM max, 66 cubic feet per minute, and the rest of the specs I'm not really all that concerned about. So since it didn't come with any other information, I went hunting and I found this Noctua PWM specification white paper, which is probably far more detailed than I need, but if anybody knows about controlling PC fans, it's probably Noctua. So there is the connector. They have specs for all 3 different voltages, but I am primarily concerned with the 12 volt one right now. So starting from the side of the connector that has a little ridge on it, we have the ground wire followed by 12 volts, the RPM, which I'm going to ignore, and then the PWM up there. And further down, they talk about the target frequency of the PWM. Should be about 25 kilohertz, but it can accept a fairly wide range, so that's not a big deal. But they also talk about the maximum voltage for the PWM signal being 5.25 volts, so basically 5 volts. Even for the 24 and 12 volt fans, so I am going to have to use a couple of different voltages here, which is a little annoying, but we shall cope with that. So there's the connector held in the orientation that they had it on that website. So I'll put ground there and plus 12 volts there. So apparently some types of these fans, if they're not getting a control signal, will just run at full speed in a fail-safe mode. And well, let's see what happens if I turn this thing on to 12 volts. Ooh, RGB. And yeah, it is running. Seems to be fairly quick. And yeah, 150-ish milliamps. So that's not too bad, but that's not generating all that much noise. My air conditioner you can probably hear in the back, and the fan of this power supply you can hear, probably louder than this thing. But it is generating a little bit of noise. And really, there's no need for it to be running at full tilt. I guess there's no harm in it either, but let's carry on and just see if we can control the speed of that, just for the fun of it. Maybe I'll incorporate that into the final project. I'm not sure yet. Now then, there are lots of ways to generate PWM, but my favorite way, and probably the simplest way, is to use the good old 555 timer. This is almost the standard astable multivibrator with a couple of minor changes. Normally, the potentiometer would be between the plus voltage and pins 6 and 7. But in this case, I've brought the potentiometer out. Pin 6 goes to the middle of the pot. Pin 7 goes to the join between these two diodes here and this resistor. And then that resistor goes up to 5 volts. So it's similar. There's only a couple more components. Let me show you a schematic of this. This is pretty much what I've got set up here. I'm running it at 5 volts because I need a 5 volt control signal. But that aside, there is my pot connected to pin 6, which also jumpers across to pin 2. That is very standard 555 timer stuff. Pin 7, the discharge pin, goes between this resistor and these two diodes. The diodes are sitting opposite directions. They're calling for a silicone diode, just a standard diode. I've got a couple of Schottky diodes in there. I don't think it makes that much of a difference. It might change the voltage threshold ever so slightly, but not so much as it matters. I'm not using this stability capacitor on the control voltage line. I don't typically. It doesn't really matter. You can if you want to, whatever. And this is the timing capacitor. I'm not using 10 nanofarad because I needed to get that 25 kilohertz that the Noctua document talked about. After some experimentation, I landed on a 472, which is 4.7 nanofarad. And that gets me close enough to the ballpark. So when I connect the scope up and adjust the pot, you can see the pulse width modulating there, and you can see the frequency is in the 27, 28 kilohertz range, which I think should be close enough. So that, I think that'll do for now anyway. So now, in order to make this work, we will join the grounds between the two circuits. So between the two power supplies, so there is the 5 volt ground coming from over here, and here's the 12 volt ground. And I'll just reestablish that ground. Well, let's use a black wire. Not that I'm that big on color coding, but this could get confusing. And then that is pin 3 of the 555, which is the PWM out. I'll just connect that to the PWM in here. That's turned on. Turn that on. What is our pulse width right now? About 65%. So theoretically, if we change this, the fan should change, and you should see things changing. You can't see the thing spinning exactly, but you can see the speed of that divided by the shutter speed of my camera here. So hopefully you'll see it change. So that is 97%, so basically full speed. So if I crank it all the way this way, not fall off there, and you see the speed changing. 25%. There's basically 10%, which is about as low as I can go. But I think, yeah, you can see the speed changing there. So it doesn't change instantly. It is still spinning, even though it looks like it's spinning backwards. So let's just bring that back up a little bit here. There we go. So that is about 37%. If I get a bad connection on here, it changes. But yeah, you can see the speed changing as I'm messing with that. So that is, I think, what I want out of this. Although, for extra points, it'd be kind of neat if it was thermostatically controlled, wouldn't it? Just to ramp up and down speed with temperature. Let's turn everything off here for a second. And let's see what happens if we move that potentiometer over one position. So it's now just acting as a variable resistor. and we replace the other side of that potentiometer with this thermistor here. So this thermistor at idle should be about 10K resistance. This potentiometer can be anywhere from 10K to nothing. So we turn that back on again. We can see our PWM over on the scope, if that camera's still working. Cool. And if we turn that on there, so now we're getting whatever that speed is. But then if we warm that up in our hand, you can see that the percentage is changing, and I think you can see that the fan is changing speed a little bit. Let's warm that up a little bit more dramatically. Well, there we go. And you can definitely see that happening. That's 73%, 72. I'm not going to cook this thing. There's 75%, and that's probably way hotter than we're going to get in the application here. I'll just cool this down relatively quickly. Actually, let's put it in the airflow of the fan over there. That should slow it down. Yeah, I think you are seeing the speed changing as that's happening. Very cool. Let's take this experiment one step further and actually see if that thermistor can do a reasonable job of measuring the output, the temperature on my heatsink over there. I'll just connect that up also to my 12-volt supply here. I've got its current limit set up to 5 amps, so that should max that out. And we'll just tape that guy onto the resistor, because if I remember correctly, it's the resistor that's hottest in this little unit here. And turn that back on, and we've got 37%. So now if we turn this on, we're only drawing that 38 milliamps right now. And if we crank up the load, there we're pulling about 4.5 amps out of that right now. So that guy should get hot pretty quickly. And as it does, you should see the PWM start to change. Yeah, we're at 40% already. And you should see the fan speed changing as well. And just for grins, we'll look in there, and yeah, there we go, 180 degrees on the resistor. What's going on down on the 130 degrees on the MOSFET, 200 degrees at places on the resistor. Okay. But as you can see, the fan is going faster, and we're up to 80% duty cycle, which tells me that this is working just splendidly. Let's actually turn that so that's blowing on the resistor. And what can we do? Oh, I guess we can turn that down so it's not generating heat anymore. So we're down to just the few milliamps that this thing is drawing, and the PWM should over time come back down again. I mean, this isn't an ideal situation. There's not very good thermocoupling there, but yeah, I think this is going to work. I'll have to put that onto a proper circuit board, but when I rebuild this, I'm going to build a new circuit board anyway. I will link to that Noctua document and the PWM page that I found that schematic on, but it's a super common schematic. If you just put in 555 PWM circuit, that will come up from all kinds of different places. It's nothing new or unique. It's a very common application of the 555. Well, that was fairly quick, fairly straightforward, but it's an experiment that I've never done. Maybe you've never done it before either, but I thought it would be fun to do. Thanks for watching. I appreciate that. Questions and comments and complaints and everything else down below as usual. I'll talk to you later.